All right, let's come back. Now we are going to discuss more on um, the numerical methods. So let's go to the final part of Newton's second law. Now we are going to discuss about a method called scaling in a numerical calculation. Why do we need that? Now, in doing numerical calculation, sometimes we encounter very large or very small numbers, right? For example, if you are calculating the motion of a satellite around the Earth, then probably you are involving distance of the order of 10 to the power 7 meter. That is a typical radius of the Earth, right? The diameter of the Earth is about that order. So you are studying a satellite, then you involve distance of that order. But suppose you are doing a calculation for say an electron inside atom, then you probably will be dealing with distance of the order of 10 to the power minus 10. That is the Armstrong, right? So physics involve a very large or very small number depending on the problem that you are interested. And it is very inconvenient to carry this big or small number around when you are doing a calculation because you are using the scientific notation and you will be involving 10 to the power minus 23, 24, or 10 to the power minus 10, 10 to the power 10. That would be very inconvenient. And also, one of the very important problem in doing numerical calculation is that we typically don't know the time scale before doing that problem. Okay, if I ask you, you go to calculate the motion of a satellite that goes around Earth once, then you may ask, what will be the time scale? What should be the typical time scale for that problem? And what delta t should we choose? Because as I say, in doing numerical calculation, you have to choose a time step, the step for iterating the equation forward. Do you remember that? You have to choose a time step to be much smaller than the typical time scale variation. And for the case of a satellite revolving around the Earth, the typical time scale is obviously the period of the satellite around the Earth. But do you have some idea about the period of a satellite before the calculation? You don't, right? You probably think, well, maybe it is several hours or several tens of minutes, or maybe several days, or maybe even several months. Before you do it, you don't know the time scale. And if you don't know the time scale, you cannot take a suitable delta t. Okay, so that is a problem. And we also encounter in physics, there are many different problems with the same physics. For example, the moon moving around Earth, the Earth moving around sun. They are all problems of gravity about a stationary object, stationary star, right? About a stationary gravitational source. They are actually the same problem, okay? But the only difference is that the mass of the Earth is very different from the mass of the sun, and so on. So we actually encounter very similar problem, but just with different scale in the mass and different scale in the time. So can we solve all this problem together instead of do it one by one? Scaling provides a solution for all this problem. Okay, we will see how scaling allows us to know the typical time scale for the problem and set the suitable delta t. And also that with the scaling, you can apply the numerical calculation for one problem to different cases. Okay. Now let's go a bit further. Okay, suppose now we know the laws of universal gravitation. Look, I think you learned in high school before. The gravitational force between an apple, for example, raised at a distance r from the center of the Earth. Okay, r is a distance of the apple from the center of the Earth, and the mass of the apple is m, small m. The mass of the Earth is big M, and the gravitational force between them is gmm over r squared. Here I put a minus sign because the force is attractive. Because the r, the increasing direction of r is outward. So an inward attractive force should be negative. Okay, so that's why I put a minus sign. But I know that if I allow the apple to fall on itself under gravity, the motion will be described by Newton's second law. So F is also equal to ma. And F is the only force acting on the object, the gravitational force. Okay, the gravitational force is now not given by just mg, but given by the exact expression of gmm over r squared, because it will change with the distance from the center of the Earth. On the surface of the Earth, we assume the gravity force will be constant, because when we go to a higher altitude, the distance between that the distance change will be much smaller than the radius of the Earth. So we ignore the distance change. We totally ignore the distance change, and we assume the gravitational force is a constant given by mg, where g is the 9.81 meter per second squared. But now, if we are considering the apple falling from a very quick height, say several radius of the Earth to the surface of the Earth, then you cannot ignore the change in distance. Okay, you have to include the change in distance, which is the change in r, in this exact formula. Now, so we now set up the equation of motion. If F is equal to ma, then I can equate this to, and I eliminate the m on both sides. So I cancel the m on both sides. So the acceleration is given by minus g big M over r squared. And the acceleration is given by d squared r dt squared. The second derivative of the distance from the center of the Earth. And the minus sign is there because we take the positive direction to be the outward direction. In the outward direction, r is increasing. So an inward force will carry a negative sign. Okay, because of the attractive force. Okay. Now for this problem, we may measure the distance by SI unit. For example, r by meter, t by second, and m by kilogram. We can measure that with SI unit, but that is not convenient. In this problem, in this particular problem, there is a natural length scale that seems to be more convenient, and that is the radius of the Earth, big R. Okay, so we take the distance as unit of R. Okay, namely, if the apple it has a distance equal to 2 times the radius of the Earth, then we denote it simply by 2. So we use R as a unit. Okay, that is a distance from the radius of the Earth as a unit. Okay, and we can also define another time scale t, and that is to be determined later. We will see how to determine it. And using this time scale and length scale R, we can define the so-called dimensionless distance and dimensionless time. Okay, so we define it at x and tau, where x is equal to small r, the actual distance in SI unit, divided by the radius of Earth. And the time variable tau is equal to the actual time, maybe in second in SI unit, divided by a certain time scale t. I don't know what t is at this moment, but let me do it. Okay. Now, you can notice that x and tau are dimensionless because x is a ratio of 2 distance. So the distance cancel. Okay. In whatever unit, the distance will cancel. The dimension of distance will cancel because it's a ratio of 2 distance. And for tau, the dimension of time will also cancel because it's a ratio of 2 time. T is a time, and the original time variable t, small t, is also a time. So when I divide the two, the dimension is gone. So they are dimensionless. Now let's see how to express the original equation in terms of x and tau instead of r and t. Now we have the first derivative of the apple as dr dt. But small r can be written as big R times x, right? From this definition. And small t can be written as big T multiplied by tau. But both the r and the time scale t, they are constant. They are some typical length and time that is defined by us. In here, we define the radius of the Earth as capital R, which is of course a constant. We don't know what t is, but that doesn't matter at this moment. At least we know t is a constant, certain time scale, maybe 1,000 seconds, we don't know. And so they can be taken out of the derivative because they are constant. And so if I take r and t out, it will become r over t dxt tau. So we express the velocity of the apple in terms of the dimensions variable, dxt tau. Okay, and how about the second derivative? Well, the second derivative is the derivative of the velocity. So it's ddt of dr dt. But we know that dr dt, as before, we know that dr dt's can be expressed as big R over t dxt tau, right? And the dt here, and the second derivative dt here can be expressed as the big T multiplied by tau. We do the same thing again. Now we can move all the constant out because the constant will not be affected by the derivative. After doing that, we will find a factor of big R squared over t squared in front. And in terms of the dimensions variable x and tau, the acceleration is given by d squared x d tau squared. Okay? So now we succeeded in expressing everything in terms of x and tau instead of r and t. We simply hide all the r and t in this constant, big R and big T. Okay. How about the gravity term on the right hand side? It is gm over r squared, but small r can be expressed in terms of big R multiplied by x. Again, we pick the big R out, so it becomes 1 over big R squared gm over x squared with a minus sign. Now we put everything back to the equation. We have this equality, right? This is the acceleration, gravitational acceleration, and this is Newton's second law, the second derivative in terms of the dimensions parameter. Now we put all those constants together. We arrange this constant such that they form a cluster. Okay, the gm are constant, the r squared is constant, the r here and the t squared, they are constant. So we put them all together on one side, and that forms a constant gm t squared over r cubed. Okay, so the equation becomes something like this. Well, we haven't defined what the timescale t is, right? We only introduced it, but we haven't defined it yet. Now it is the time to define it. We should define t, the timescale t, such that this branch of constant is equal to unity. We can define whatever t we like. We haven't defined it yet, right? T is something that we want to define arbitrarily. We can define arbitrarily. And we now will like to choose to define it, the t such that this branches of constant is exactly equal to unity. And why do we want to do that? Because we want to simplify the equation. If I define it to be U1, then the equation of motion can be simplified like this. D squared x dt d tau squared equal to minus 1 over x squared, which is very simple. I get rid of all the constant by defining t to be this quantity. Of course, I can solve for t, and t is just the square root of r cubed over gm. Okay? By defining the t to be like this, I get rid of all the constant and all the ugly constant, and I end up with this very simple differential equation that involves only x and tau, which are the dimensions variable. Okay. Now suppose the object, suppose in this situation we want to find the motion of the apple falling from a great height. How great is that height? We suppose the apple to be released at a distance 2 times the Earth radius from the Earth center. We're supposed to release it from 2r, the distance 2r from the Earth center. So what is the initial position in terms of the dimensions parameter? In terms of the dimension distance, what is that? We know that x, the initial x, is the initial r divided by capital R. So it's 2r divided by r, and so the r will cancel. And so initially, the object is at the distance 2 in terms of this dimensional length from the center of the Earth. Okay, so we use this as an initial condition. And also, since the apple is released from rest, okay, so the RDT is 0 at the beginning, right? And since the RDT is just proportional to the XD tau, they are just different by constant. So the XD tau is also 0 because the apple is released from rest. So I have these two initial conditions. And these two initial conditions allows me to iterate the equation of motion, to integrate this equation of motion forward. I just do the same thing as before, like just like solving any kind of motion that I give you to do in the previous homework. But I don't have to care about the constant. I only have to deal with a simple equation where acceleration is simply given by 1 over the distance squared. That will be simplified the problem a lot, okay, with this initial condition, okay. So I do this the calculation, and I do it on spreadsheet. The acceleration is simply given by 1 minus 1 over x squared, and it's in this column, right? And the initial position is 2, initial velocity is 0, and I do the iteration calculation as before. And I found that when I plot a graph of x versus, this should not be t, actually, this should be tau. Sorry about the typo. I should write x against tau. And I find that after doing the calculation, I find that the distance decreases like this, okay? And eventually, when the apple falls on the surface of the Earth, x is equal to the radius of the Earth, right? X is equal to 1 because the distance is now equal to the radius of Earth. So R divided by R is just 1. So X is equal to 1 means the apple is now reaches the surface of the Earth. So I want to know what is the time here. I can read from here the time. And I find that happens at the time tau equal to 2.57. And the dimensionless velocity I read from this column is minus 0.990. That is a reading I read from the table. Now, don't rely on the graph. The graph is not accurate. You go back to the table. You find the position x equal to 1 in the x column, and then you look at the time, the corresponding time, and I find that this value. And when you look at the dimensionless velocity dx tau, I find this value. Okay, so that's how I solve the problem. Now, after doing the scaling, you see the equation is very simple. It becomes d squared x d tau squared equal to minus 1 over x squared. It does not carry any large or small constant, right? So you expect if the initial condition is not that large or that not too small, you expect that that in the calculation, you will not involve a large number or a very small number. You will involve number that is of the order 1, right? Everything should be of the order 1, right? You start with x equal to 2 and the x d tau equal to 0. So you will be expecting something, some of the changes will be maybe 1 or 2 or 3. It may be as small as 0.1, but it will not go to 10 to the power minus 5 or 10 to the power 7. It will not go to a very large or very small value, right? So you know the time scale. The time scale is exactly 1 of this problem, exactly 1. So you better choose a time scale that is much smaller, a time step that is much more than the time scale. So here I choose it to be 0.02. 0.02 is much smaller than 1. Because I expect here, the typical time scale that the things happen will be order of the 1. And this is exactly what I observe. After 2.57, the time, it falls to the surface of the Earth. Okay, so I should choose my delta t should be much more than this time, and that's 1. And that's a 0.01 in this case. Now let's calculate the time scale. I know the radius of the Earth, right? I know the gravitational constant, and I know the mass of the Earth. So I can know the time scale tau, the time scale t. The time scale t is 805.7 seconds. So after I read out the dimensionless time, I multiply it with the time scale, I get the true time. I convert the dimensional time back to the more convenient time we use, and that is the second. Okay, I simply multiply big T with tau, I get the real time. And also, how about the velocity? I know that the dimensionless velocity dx tau is related to the real velocity dr dt. What I mean by real velocity, I mean the velocity expressed in SI unit, meter per second, okay? And the dimensionless velocity, you know, is dx tau. And they are related to each other by a constant r over t. So I put in the constant r over t, the radius and the timescale t, and I multiply it with the value I got from the calculation. I get the true velocity in meter per second. Okay. Now suppose now the falling does not happen on Earth, but the same calculation happens on Mars, on the planet Mars. Okay, and initially I assumed that the apple also falls from a distance of 2 times the Mars radius. So everything is the same, except I now replace the planet Earth with the planet Mars. Okay, so do I need to do it again? No, I simply change the scale. Now for the time scale, I should use for the space scale, I should use the radius of Mars, but not the Earth. And for the time scale, I use this equation. And this equation says I should divide the cube of the radius of Mars. Now this is the radius of Mars, not the Earth, by GM, where M is now the radius of Mars. It's not the Earth, right? And take the square root, I will get a time scale T. And it happens for Mars, the time scale is 9.6 seconds. So the calculation is the same, because the calculation does not involve the mass and the radius of the planet, right? So the calculation remains the same. I can still use my dimensions time and multiply by the new time scale, and I get the time corresponding to the actual falling time of an apple to the surface of Mars. Okay, so it's a very powerful method. I solved not only one problem, but a whole range of different problems. Okay, so that is the idea. I better have a pause here. Do you have any question about what I'm just said? Any questions? A little bit of stop here because I'm going to a new chapter. If you don't have any questions, never mind. You keep thinking yourself, and if you have a problem in doing your homework, please let us know. And the TA are there in the exercise class and also the consultation hour. If you have problem, you simply go to the consultation hour to find them. There are convenient links on the blackboard. So at the consultation hour, you click those links and you can meet them directly on Zoom. Okay. And if you have other problems that you find you will be more happy with talking with me, then you simply send an email to me, and you can also make an appointment with me on Zoom so we can discuss it on Zoom or even after class. Okay. Now we come to a new chapter on energy, on work and energy. Do you know what is work? Work is something a very weird concept. What is work? Is work a kind of energy? Is work done a kind of energy? Now the answer is not. Work is actually not a form of energy. Work is the energy transferred by the application of force. So that is the process of energy transfer. Just like you have some money in your pocket, and I have some money also in my pocket. And now I give you $100. Okay. After I give you $100, it becomes the money in your pocket. In my pocket, I lose $100, and in your pocket, you gain $100. Is that right? So these are different forms of energy. Maybe I represent the potential energy, and I give you $100. You are the potential energy. You are the kinetic energy, and so you have an increase in kinetic energy, and I have a loss in potential energy. But when I give it to you, that involves work done by a force, and that work done is a process of transferring those energy by the application of a force. So work is not a kind of energy itself, but it is a process. It is the amount of energy that is transferred through the application of a force. So the work done on the system will be equal to the change in energy of the system. Because I give you some energy, that means you have more energy. I give you some, I do some work on you, that means I give you some energy, and so you have more. Okay, so that is called the work energy theorem. Now, how do we define work? The elementary definition of work we have discussed before is defined by a dot product. It's defined as Fs cosine theta, where theta is the angle between the force and the displacement. When a force applied on a moving object, and the object moves a distance s with a displacement s, the dot product F dot s, or Fs cosine theta, give you the amount of energy transferred to the object by the force. Okay. And the unit of work is joule, is same as that of energy. And from this equation, you can easily see that joule is equal to the unit of force, which is Newton, multiplied by the unit of the displacement, which is meter. So Newton meter is joule. Okay. Now, but this definition is valid only when the force is constant. We assume that the force doesn't change in direction or magnitude during the motion. And we will extend it to a variable force in this chapter. And we will not discuss about generalization to 3 dimensions. Sorry about that, because mathematics will be too complicated for E1 student. So we only discuss about the 1-dimensional case with a variable force for work done. Now, suppose the force is changing when the object moves, okay? And we divide the displacement of the object into certain section. Maybe at a certain instant, the object is there, I call x1. At a slightly later instant, the object is x2, and x3, x4, x5, so on and so forth. Now we choose the represented point in the interval from x1 to x2. And in this space interval, the average value of the forces acting on the body is F1. Now, if x1 and x2 are sufficiently close to each other, then the value of F1 doesn't change much. Okay, it's a good approximation over the whole interval. Is that right? Similarly, if I choose F2 to be representative force in this time interval, in this space interval, then I assume that x2 and x3 are very close together, so the force is almost equal to F2 without any changes inside the interval. And so we have x3 and f4. So the work done for the first interval will be f1 delta x1, where delta x1 is x2 minus x1. And I have f2 multiplied by this interval, which is x3 minus x2. I call it delta x2. And we have, again, f3 delta x3. And I sum it up to n step. I suppose the whole line is divided into n step, up to fn delta xn. So I form a summation of f multiplied by delta x. Okay, the I here is an index for the summation. The I is from 1 to n. So I now divide the whole axis, whole displacement into n step. Okay, and of course I would like to know what is the limit when delta x, when each of the step is very small. now I defined it into many, many small steps. And for each of the steps, the delta x is tends to 0. And so I think you know what it is. It's the integral. The work done will become an integral of f over x. Okay, so that is the common definition of an integral. Okay. Now, if you plot a graph of f versus x, okay, the f may change like this. Okay, suppose f is changing with x like this, and the force in the I step will be Fi, which is this value. Then delta x will be a small space interval covered by the object in this interval. And so Fi multiplied by delta x will be the area of this vertical strip. And if the delta x tends to 0 in each delta x tends to 0, then this will become integral of f from a certain starting position to a to a certain ending position b, and that is represented by the integral. And the integral is graphically represented as a curve, as an area bounded below by the fx curve. Okay, so if I plot f again x, this is the area of a one strip, and if I sum up all the strip, it becomes the integral. And the integral, it just means the area enclosed by the curve. Okay. Now suppose now we play with a spring. A spring is a coil that you can stretch it or compress it. Okay. And suppose the spring obey Hooke's law. Hooke's law says that the force is proportional to the extension of the spring. If the extension of the spring x is large, if we stretch the spring to the right, then with extension x from the equilibrium position, then the force will be equal to Fx, where equal to Kx, where K is called the spring constant. The spring constant depends on the property of the spring. If we have a tough spring, very hard to pull it apart, then we have a large K. Okay, you only need you need a very large force to make it extend a little bit. Okay, if we have a next spring, then the value of K will be small. Okay, so it depends on the property of the spring. Okay, and it's a constant, a certain constant for a certain spring for a wide range of x. Okay, so that is a simple model. Now we also include a minus sign here, because when we apply external force, the external force we put object and we stretch the spring, and so the object move a distance x along the direction of the external force. The force from the spring will be tending to pulling me back, right? So it will be in opposite direction to the external force. Okay, so I would add the minus sign. The minus sign means the force from the spring is actually in the opposite direction to the displacement of the block, which is the extension. Okay, so I have the equation F equal to minus Kx. Now, in order to pull the block out and pull it out, I have to apply external force, just balance the force of the spring. I don't want the block to accelerate. I just want it the force to be balanced so I can put it out slowly. And so I apply external force, which is equal in magnitude to the force on the spring, but in opposite direction. So the external force will be given by minus F, and since F is equal to minus Kx, it will become plus Kx. So the external force is equal to the force on the spring, but it is in the same direction as the displacement. That is my pulling force, the force from my hand. Okay. Now I want to calculate the work done by the external force in stretching the spring by an extension x. So I integrate the force from 0 to x over dx. And since the force, external force is plus kx, I put in plus kx, and the k can be taken out. Now I integrate x over dx from 0 to the final displacement x. So I get half x squared. So together with k, I get half k squared. So that is the work done by the external force. If I stretch the spring by extension x, the energy that I have to input to the system is half k squared. Now you can see from this diagram why the work done is half k squared. Now the horizontal axis is x, right? The vertical axis is external force. And external force just balances the force of spring, so it's given by kx. So that becomes a straight line, right? Because the kx is just a straight line with a slope a, k. Is that right? And this integral simply gives me the area bounded below by the curve. This is what we say for the work done. The work done is the area bounded below by the fx curve, right? So this area is the area of the triangle. What is the area of triangle? Is equal to 1/2. The base of the triangle is x, where x is the final displacement, and the force, the final force is kx, right? So the height is kx, the base is x. So 1/2 the height of the triangle multiplied by the base will become half k squared, just like we found with the integration. Okay. Now we study another example, which is somewhat more difficult, and that is the gravity problem that we have just mentioned in a previous chapter. We have an apple, okay? At a certain instant, it is at a distance small r from the center of the Earth. If I let the apple to, if I release the apple, then it will fall under Earth gravity, right? Because the Earth gravity, the back arrow is pulling the apple inwards. Okay, so this is the force of gravity, and the force of gravity is given by minus GMM over r squared. Because we take the outward direction as positive, so inward force has carried a negative sign. Okay. Now, if I want to prevent this apple from falling, if I just want to hold this apple, suppose I'm a Superman, and I want to hold this apple in space without letting it to fall, then I have to apply an external force. And the external force has to be balancing the gravity force. So the external force is the opposite of this gravitational force. So it's plus GMM over r squared. So the external force is outward, but the gravity force is inward. Okay, so they're in opposite direction. Although they balance each other, they are in opposite direction. Now I want to find the work done by the external force. So what are the starting point and the ending point? Suppose I'm a Superman, and I want to transport the apple from a point which is very far away from Earth to the distant r from the Earth center. So I do the work done from infinity, from a point which is very far away, that is essentially infinity, to a position which is at a distant r, small r, from the center of the Earth. And I want to calculate that work done. The work done required by the Superman in moving the apple from infinity to a certain distant r from the center of the Earth. So I do this integral. Now, why the Superman needs to do this? That is unimportant. And eventually we will identify that work done with the potential energy. Okay, so it will be better if we consider the external force as for the work done. Okay, so now I consider work done by Superman, and it's given by this integral. And now we know that the external force is GMM over r squared. So I integrate this. Now, how do I integrate this? Now, this is r to the power -2, right? Because 1 over r squared is r to the -2, power -2. So if I integrate, I will have r to the power -2 plus 1 divided by -2 plus 1. That is the rule of integration. So I then get -1 over r That is the integration result. If I evaluate this integration result at infinity at r equal to infinity, then this term is 0. Because when r tends to infinity, 1 over r is 0. So I do not have the lower limit. The lower limit term vanish. The upper limit term simply give me minus GMM over r, where r is actually the final position of the tadpole. Okay. Now you can notice that the work done is negative. Why is it negative? Because the apple is now moving from infinity to this position. So it's moving along the pink line, the pink arrow, you see that? But my external force is in the opposite direction. It prevents the apple from accelerating downwards, right? So my external force is holding the apple, preventing it from being accelerated by the gravity of Earth. So that means the external force is in opposite direction to the motion of the apple. So that's why the energy, the work done is negative. And work done that's negative means the energy is not inputted to the apple. It's somehow being extracted from the Earth apple system. So the energy goes to the Superman. It's not from the Superman to the apple, but from the apple Earth system to the Superman. Okay, so the work done is negative. Now we will see how this negative work done related to the potential energy in the next lesson. But I have to warn you about this integration. Now this integration is essentially I integrate the external force from infinity to r. I integrate GMM over r squared from infinity to r. If I swap the lower and upper limit and I introduce a minus sign, then you will see that it is equivalent to this integral. Now this integral, I simply reversed the upper and the lower limit. Instead of from infinity to r, I'm from r to infinity. But then I'm wrong with a minus sign. So I add a minus sign here to cancel. Okay. Now what is this? Minus GMM over r squared is a gravitational force. So the gravitational force plot against r will be something like this. This is the curve for the gravitational force. It will be negative, and when r goes to infinity, then the force will be 0. When r tends to 0, the force will be negative, goes to negative infinity. Okay, so integrating this negative force from a certain r to infinity will give me this area. The pink area is the integration result. Is that right? Now, but some of you may be tempted because just look like if I multiply the force by the distance, then I will get rid of one of the r, and I'll get a correct answer for that. But that is totally wrong. Why? Because it's conceptually wrong. The r here is not the general r, but the r at the final position, which is here. The force is also the final force, right? But not the force in general over the whole journey. So the final force multiplied by the final r is just the square area. This rectangular area here. And it just happened that this area and this area are equal. There's no guarantee that these two areas are equal. It just happened in this particular example that these two areas are equal. But that totally does not make sense to write the work done like this, because the work done is a continuous process. You have to consider the work done by the Superman in holding the apple step by step from infinity to the present position. You have to do an integration. You cannot just multiply the final force with the final distance from the center of Earth to find the work done. So this is totally wrong. So don't write this in your final exam. Otherwise, I will simply put a cross, okay, in your math. And the answer just happened to be the same, but the method is totally wrong. So always resort to the integration here. So I better stop